All right, everybody. We've been talking through computer networks and we've gone kind of from the physical layer all the way up to the top. Um, and what we're going to do is take some asides now, talk about some compression techniques today, and then we'll move on to crypto in the following weeks. So, why do we need to talk about compression? We need to talk about compression because it is another way to save the network. If we transmitted, say, everything all at its full uncompressed level. Those are bits and bytes that we could save in certain places. And endpoints should compress if they can. When you download your games, when you download images, they're all coming in these compressed formats that we unzip and explode out into their full form. And what we're going to do is we're going to talk about some of those techniques and what they look like. This dates back to the earliest forms of connection as we're trying to save bits to send things over really small pipelines. So let's get into it. All right, the first kind of compression we're going to talk about is called run length encoding. The basic idea here is that when you see the same symbols show up in a row, instead of just repeating those symbols, what we're going to do is we're going to shortcut it and count them instead and send those numbers. So let's say in this example, we've got 3 A's, 2 B's, 1 C, and 4 D's, and we're going to use this example several times. If you send these uncompressed, you have to send 10 bytes. Now, 10 bytes is not a lot, but you can expand this. Maybe you have to do this a billion times, and then that makes it 10 gigabytes, right? So how we run length and compress something like this, if we look at the byte level, is we say, okay, we have 3 A's, 2 B's, 1 C, and 4 D's. And at the base level, if you're still sending each of these things as a byte, we've decreased this 10 bytes to 8 bytes. Now, that's not a lot, but if you look more closely, we only need to send a number all the way up to 4. And numbers 1 through 4, 4 numbers only take us 2 bits. So 2, 4, 6, 8, at the worst, this could actually be 5 bytes. Another thing to notice here, though, is that there are certain situations in which this compression scheme actually increases our sizes here. And this especially happens if there's high variance. So if these symbols aren't appearing in a row very often, then run length encoding isn't going to do you well. And that's something to be aware of. But run length encoding is pretty awesome, especially for any regions where you have large homogeneous zones. Those are regions where everything is the same. So you imagine if you wrote a note on a piece of paper and you took a picture of that, most of the paper is white, and then you have some print on it. So you're sending a large amount of white data. So instead of sending this full image with all of these repeated white pixels, you can heavily compress that by saying, hey, I'm seeing the same symbol many, many times. So I'll just say how many times I'm going to see it, and then I'll send the symbol itself. Often you can see huge savings in compression with this. This was used in faxes and early things. Amazing stuff. And most compression algorithms use some form of run length encoding, even if it isn't the basic version that you see here. It might be something more generalized. What's next? Next up is differential pause code modulation, or DPCM. DPCM is pretty cool. So the idea is that I'm going to send a base character like A. So I'm using this same string A, B, C, D here. And then I'm just going to store references or offsets from this. This isn't a word. There we go. References or offset from that symbol. So I'll send the A, and then everything is a reference or an offset from that. So you might see something like this stream turns into A, followed by 3 zeros, 3 ones, 1, 2, and 3 threes, which are how far offset from A we are. So if each of these characters is 1 byte, then the original thing is 10 bytes long. But we can encode these numbers, again, as just 2 bits. And so when you add all of these up, you only need these 20 bits plus this reference image, which gives you 28 bits total compared to the original 80 bits. So this can be really huge. DPCM is kind of the basis in a very vague way of a lot of image compression. Once this difference becomes too large, then we just start a new reference symbol. And usually we don't think of image compression as DPCM, but it is kind of the same idea. A variant of this is called delta encoding, and each symbol is a reference of the last. And so you have to first send the A reference, but then every other symbol is a reference off of the A. So 0, 0, and then 1, 0, and then 1, and then 1, and then 0, 0, 0. And what you'll notice with this is that if we only need numbers of 0 and 1, then we can store that in 1 bit. And so this might be 1 byte plus 9 bits, which would be 17 bits total, which would be kind of amazing. And everything is a reference from the last thing. So you have to send the first thing, which are A's. And then when we see this B, it's one different than A. So we have to send a 1. But then when we see this B, it's 0 different from this B. This C is 1 different than that. This D is 1 different than that. And then everything else is not different from that D. So you get zeros. This is kind of amazing. Now, 17 bits is probably a little misleading, and you're probably not really going to be able to get away with this. But delta encoding is again, in a hidden, sneaky sort of way, this might be a basis for how we see some other things. And don't forget that we can still apply run length encoding after we do this. I don't know that you'll get much savings in this particular case because this is so tight. If you treat these as 2 bits instead of 1 bit, or however many bits you need, then it might get a little bit different. You can imagine an image that's slowly changing, right? Where this is super useful, a gradient image, then you might just be able to slowly change this. And the most of the image is zeros. And if most of the image, not the image, but most of this encoding is zeros, and if most of it is 0, that's already going to be great for run length encoding when you're done with it. All right, let's move on to the next one. Our next one is LZ compression. LZ compression turns out to be so huge that it shows up like everywhere. It's used in the compress command in Unix and in gzip, the GNU zip utility. It is a dictionary-based method. You can see this in GIFs, some early GIFs or GIFs, whichever you like. Basically, the idea is we can send a dictionary of symbols and then index into that dictionary of symbols. So I decided to make a different example to start so that you can think of this in a normal dictionary way. Imagine you had the words bad, daddy, cab, and you knew that they were in a dictionary with certain indices. On a Unix system, you might actually have a literal dictionary that you can look up. And in this case, let's say we made up this fake dictionary entry just for this example. Then what we can do is bad is 0, 0 in this particular index. Daddy is 1, 0. Cab is 0, 1. And suddenly these 11 bytes become just 6 bits to send the whole thing. Now, I'm hiding a little bit here in the sense that maybe we had to agree on this dictionary ahead of time, or maybe you have to send that dictionary. So let's use a different example. Let's go ahead and use our A, B, B, C, D, D, D. Imagine that we have to send these 4 bytes first, which are entries into our index table. So that's 4 bytes that we have to send at the start. And then what we can do is just send 0, 0, 0, 0, 0, 0 for the A's, 0, 1, 0, 1 for the B's, 1, 0 for the C, and then all the 1s for the D. And then suddenly this becomes 20 bits plus the 32 bits that we had to send to kind of instantiate the dictionary. And this whole thing becomes 52 bits instead of 80 bits. So it's another form of compression. Also, you should note that if we pick our indices well, that we can get quite a bit of run length encoding that helps us out here. Lots of bits showing up in a row. And actually, there's probably a couple of other things that we could do here. So this index where we store this thing first and then index into it is super huge. And it is one of the primary reasons that GIF works so well. So take a 256 by 256 image where each of the red, green, and blue channels are 1 byte. Then what's going to happen, and I'll switch to a pointer here so I'm not drawing on this. The uncompressed version of this image takes up 196,000 bytes. And that's the 256 times 256 pixels times 3 bytes per pixel. So you multiply these 3 numbers together, and that tells you how many bytes. Now, what we do in the compression is say, hey, let's limit this picture to, say, 16 colors. That might not sound like a lot, but you can do a lot with it. Maybe not amazing things. And then what I'm going to do is send those 16 colors as my dictionary. So I have to send these 48 bytes because I have to send R, G, and B of each 16. And then every entry in the image, this 256 by 256 table, is a 4-bit index that looks up into this table to tell me what the actual color is. So the number of things that I have to send are, I have to send the table itself, and then 256 times 256 times 4 bits each, or a nibble, which is half a byte each. And in total, I only have to send 32K bytes. So this same image, it's the exact same image. It just has lossless compression, which means I don't lose any data. So it's not like when you see some of these really crappy images that have these artifacts in them. This is completely lossy. I'm not losing any data here. I'm just compressing it in a smart way. And this is nearly 8 times compression. This is amazing, right? Or at least 6 times, right? More than 6. There's so much more that we can do with images. The book talks about DCT, which is a discrete cosine transform, but wavelets do a lot of work these days. And tucked away in these ideas are delta encoding, this idea that nearby pixels are similar, and we can actually quantize that difference and throw away that difference if it's small enough and things like that. It's super amazing, cool stuff. Okay, all right. Next page. So next thing we need to talk about is something called Huffman coding. Huffman coding is used in a lot of ways to reduce the number of bits, and it works on frequencies. So what we're first going to do is kind of see what frequencies of bit sequences show up and what those look like, and then kind of form a table out of it. So the way we do that is like A shows up 3 times, B twice, C once, D 4 times. And I'll take the smallest 2 numbers and I'll group those together, and I'll do that in a repeated fashion until I get a tree that looks like this, right? And what this tree says is that, with frequency 4 on the right, this should have the smallest encoding. But down here, these things that show up least frequently, they should have a bigger encoding. And if you invert the tree and then you label lefts as 0s and rights as 1s, then what you have is an encoding table for the bits. So in this example, D's are going to have an encoding of 0. You can see that here. And then A's are going to have an encoding of 1, 0. So you can see that through this path. And then C's are 1, 1, 0 and B's are 1, 1, 1. So C's are 1, 1, 0 and B's are 1, 1, 1. And that's the bits that we'll use for A, B, C, and D. So when we go ahead and encode this thing here, what we're going to have is 1, 0, 1, 0, 1, 0. There's 6 bits. And then we'll have another 6 bits for the B's, that's 12. Then we'll have another 3 bits for the C, that's 15. And then the D's only add 4 more bits for a total of 19 bits, which is a huge savings, over a 4 times savings over the original 80 bits. So Huffman coding is sometimes used to kind of reduce this number of bits up front. And then you can go ahead and apply other compression techniques to this to make this even better. You can see that there's a good index here. There's a good run length encoding. Here and here, and this thing probably compresses down pretty darn small once you apply all these different techniques. So why do we bring up Huffman coding, especially? And that's because most of the zip file formats support this form of compression called DEFLATE. And hidden behind DEFLATE are basically 2 things that we've just talked about. The first is we'll do this bit reduction using Huffman coding, like we just talked about. And then we'll run an LZ on it. We'll create a dictionary based off of that. The particular LZ method that they use is called LZ77, and sometimes you can use different ones. But generally, what you do is you have this sliding window that uses distances and length comparisons to try to figure out like what the smallest actual dictionary usages should be. They consider it kind of a generalized run length encoding, but it is really LZ. And yeah, and that's compression. Jeez, that's a lot of stuff. That's it. That's all we got. Jeez, that's really quick. So run length encoding is kind of like counting how many things show up in a row, and then instead of repeating all of those in their full form, we make it shorter. And then differential pulse code modulation is about referencing a symbol and then using an offset. And the delta encoding is referencing the last symbol always. The last symbol is always the reference. LZ compression is about using a dictionary. And then Huffman encoding is about making a table of frequencies to figure out what the right actual encoding is for your symbols. Very amazing stuff. Combine all that together, we can often get like 8 times compression in our data. So if you only have a very small pipe, like say a 300 baud modem, you might be able to get 8 times as much information if you apply some of these techniques, which is super amazing. Okay, this video got really long. We want to come in right under 15 minutes. So as always, take care of each other. And in order to do that, you have to take care of yourself. See you all later. Bye.